As the world shifts to an electricity system which depends deeply on wind and solar, the focus has shifted to long-duration storage. My guest this week is Mateo Jaramillo, co-founder and CEO of Form Energy, the developer of low-cost, multi-day energy storage solutions based on an iron-air battery chemistry. Please join me in welcoming Mateo Jaramillo to Cleaning Up. Before we start, if you're enjoying Cleaning Up, please make sure that you like, subscribe, and leave a review. That really helps other people to find us. To make sure you never miss an episode, subscribe to us on YouTube or your favorite podcast platform, and follow us on Twitter, LinkedIn, or Instagram to participate in the discussion. Also, you can visit cleaningup.live to access over 160 hours of conversations with extraordinary climate leaders. And you can subscribe there to our free newsletter. That's cleaningup.live. Cleaningup.live. And if you particularly enjoy an episode, please spread the word, tell your friends and colleagues about it. Cleaning Up is brought to you by our lead supporter, Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation. So, Matteo, welcome to Cleaning Up.
Thanks, Michael. Great to be here.
Very good. Now, I've done my very short introductory blurb, but I'd like to hear in your own words, who are you, what you do?
Okay. Well, my name is Mateo Jaramillo. I am the CEO and co-founder of Form Energy.
Let me say, Form Energy, we're going to get into all the detail. It's an iron-air battery. And how did you give a sort of thumbnail bio? Okay, what were you doing? Where did the idea come from?
Well, I've been in batteries now for about 20 years, so I've been thinking about energy storage that whole time, and specifically for the grid. There's sort of two branches of energy storage in the world these days, and one is most focused on the automotive space. And I have to admit, I've never been a wrench turner under hoods. That's never been my fascination. So I wasn't brought to the field through the automotive lens, but rather for some reason that I can't totally explain, I just seem to be fascinated by energy storage on the grid. It just seems to be an area that I have a lot of curiosity about, and I'm super lucky to have found that professionally. So I've been doing that for a long time, and I was at a company in New York for a number of years, and I joined a little startup called Tesla in 2009. We were 300 people then, and I left at the end of 2016. We were about 30,000 people, and without really a specific idea for what was going to come next, except that I knew that I really wasn't very good at thinking about much other than energy storage for the grid. So continuing on that thread, and that's what brought me here today.
Right. Now, you used a really nice phrase I've not heard before. I wasn't a wrench turner under the hood. Now, most people would use the phrase, piston head or petrol head for a car person. But of course, they're not really, there's no pistons and no petrol at Tesla. But you were not on the automotive side at Tesla, were you?
That's right. I was on what we called the Powertrain side of things. So that was the group that was headed up by J.B. Straubel, who was my boss and one of the co-founders and CTO at Tesla. And it really is sort of the core technology of the company. But, well, maybe not as much any longer. It's a phenomenal manufacturer and automotive company now. But originally, the guts of the company was really just the powertrain, the battery, the drive inverter, the motor, and the control systems that sort of tied that all together. And when I joined, we only had one car, of course, the Roadster, and the chassis, the rolling chassis, as it was made by Lotus in the UK, of all places, and flown from sort of improbably flown from the UK over to California, and then we put in the powertrain there, and that powertrain technology really was the foundation for the company, and launched, of course, many vehicles beyond that.
Right. Now, we had one of the investors, early investors, Nancy Fund, who came on the show, and she talked about some of those early years. She did not mention that you were actually flying those Lotus chassis over to California. I did not know that.
Oh, yes. Yeah. They were pushers, as they're called. They just sort of rolled on the wheels, and they were rolled onto the planes and rolled on.
Right, but you started the Powerwall business, so what you call the Powertrain in wrench under the hood terms, that's the battery, and then getting that energy into the wheels. But you took the same battery technology and applied it to these Powerwall home energy storage units, correct?
That's right. And I was part of the Powertrain team there because I saw the possibility for lithium ion on the grid in 2009. To me, that was obvious that was going to happen. And Tesla had all the required components to be successful there. They had, of course, the pack, not just the cell and the pack technology, but the controls, the inverter, everything really. And JB brought me in to run the Powertrain business. We were already doing work. We had a contract with Daimler that we were delivering on, which we built on successively with Toyota, as well as other projects with Daimler. But my night and weekends job was to start up what became the Tesla Energy business, but which was essentially just sort of a skunk works internal to Tesla at the time. And what we did is we applied for some grants. We sort of made sure that it was fully self-funded. We weren't requiring any sort of corporate dollars to do that, and we modified automotive battery packs and control systems so that we could deploy them on the grid. And so we did projects very early on in California, the S-chip program, which you're probably familiar with, the self-generation incentive program, which from California spawned a number of great sort of initiatives there. Really drove the early deployment and acceptance of lithium-ion grid storage, and we fully took advantage of it.
So it may be hard for people to kind of spot the extraordinary statement that you made, which was that you thought it was inevitable that lithium-ion would get on the grid, would be grid connected. I mean, we're talking 2009, 10. I mean, these were little batteries. These were, these were this size batteries that were powering, like, I don't know, it was probably a little bit past the camcorder stage, but not that much. And, so it was a huge leap for JB and for Elon to say, this is the car technology of the future. But the idea of racking these up in vast numbers and sticking them on the grid is pretty extraordinary.
Well, like I said, for some reason, grid storage is just an area of fascination for me. And I thought about it a lot, and it just, one seemed to follow the other as night follows day, and then day follows night. It just seemed really, really obvious to me.
And there are gigawatts and gigawatt hours of lithium-ion batteries connected to the grid. But but you've made a jump. You've made a jump from Tesla, and you've made a jump to a different technology. Can you talk about those, perhaps in turn? Why, okay, so you're fascinated with grid storage. Why not? You've got this fantastic platform. Why not stay with Tesla? I mean, isn't that the obvious thing to do?
Perhaps it is the obvious thing to do. And Tesla is a platform. It's an amazing platform for a lot of things today. Of course, they have the whole AI initiative, and they've got, deep manufacturing expertise now. And so it is truly a tremendous place. And at the same time, I like a earlier, scrappier environment. And like I said, when I left, the company was 30,000 people. It's now well over 100,000 people. It's just a fundamentally different type of entity to operate in. And as scrappy and innovative as Tesla is, sometimes even still the bureaucracies of a 100,000 person company, even when it's run by Elon, can get in the way. And so I wanted to, walk through the fields a bit more, I suppose, and think about truly what would come next after lithium ion. And a lot of my conversations starting up the Tesla Energy effort were with the utility executives that were buyers of lithium ion, large utilities in the United States. And over again, I heard the refrain, we'll do lithium ion. Yeah, sure, we'll figure it out at some point. This was still when we were trying to figure out the exact puzzle piece of the business case. They were pretty sure they would do it, but they also would reference the biggest problem that still had yet to be solved, which was how do I replace the capacity in my system that is retiring today? In other words, how do I do something about the coal capacity and even natural gas capacity that's going away? And they would sort of say, well, until you can really address that problem, storage is going to be somewhat limited on the grid. And so that was sort of the idea that I carried forward after I left Tesla.
Right, and we'll get on to the solution you came up with. I just want to stick for a second with, because it is such a sort of fascinating and iconic company, Tesla. What is it about? I mean, both JB, he's now doing redwood materials, so he left to do that. You would have said, well, why not do that within, Tesla is must be pretty much the biggest user of batteries in the world at this point. Why not stay there? You've left because, okay, you want to do longer duration storage, but again, it could have been perfectly integrated with the Powerwall business. What is it about Tesla that people leave?
People leave Tesla for all sorts of reasons. It took me 3 tries, to be clear. When you're that deep into it, sometimes it's hard to sort of even comprehend what's happening outside of it. So there's a very strong gravity about the place, to be sure. It's not like you just sort of eject out of there frictionlessly. It took me a couple of tries, like I said, and JB's there for a tremendously long time. And his mark is indelible. But 7.5 years for me was long enough. It's an incredibly high rate of work that happens there, is probably the generous way to put it. I'm married. I have 3 kids. I would love to stay married and be in my kids' lives. And so, sometimes you just look for something a little bit different. And Elon is, as great as he is, there are downsides to the company. And for me, one of those downsides was just sort of the size and the growth. And I like I said, sort of going back to the earlier stage and figuring things out from the very first steps.
So you decided to leave for an easier life, is what I took away from that. And you decided to become an entrepreneur.
Yeah. Well, yeah. Maybe just say, I wanted the balance to be a little bit different. And Tesla will always ask for more, right? That's sort of the nature of it. And I like to work. I'd love to work, in fact. But I also love my family, and I needed to be able to integrate those 2 things in a way that I just couldn't do that at Tesla. And I don't work any less for sure now as an entrepreneur, but I work differently, and I work in a way that allows my family to be part of the journey with me.
Right, and you have all of the good things about entrepreneurship. The bad things is that all the stress and the working all the time. Frankly, I mean, I've done it, but you do control. I mean, at the end of the day, you are in control, and when you do score a win, it is your win. So, talk to me about then the technology choice, because so you've honed in on longer duration, but that doesn't narrow things down very much, right? Because we've got seasonal storage, we've got even and it goes all the way up to multi-year, where you can have a bad wind year and suddenly, the energy system's not going to be able to cope. But at the other end, you've got the kind of lithium ion, which is great for, a few hours. So how did you choose a spot within that? And how did you choose the technology that went along with it?
Yeah, you're right. The solution space is incredibly broad, and especially, the term that you hear a lot is long duration storage, but that term covers everything from perhaps 6 hours of lithium ion to, as you're saying, thousands of hours of geologic hydrogen, for example, geologically stored hydrogen. So you do need to narrow this space a bit, and I was sort of keeping that refrain in my head of these utility executives, like, how do I replace the function of these things that I know I'm going to need to be able to replace? And what I did was essentially I'm a native Californian, born and raised, and was living in California at the time. I've since moved to Pittsburgh, Pennsylvania, but I know the California grid probably best. And more as a thought experiment than anything else, I just started with the California grid, and I said, if you wanted to replace the function of the thermal generation on the grid, what does that look like? And 100% of the thermal generation in California is natural gas. And so you essentially have a very gas-heavy grid, and then you have a very renewables-heavy grid. And I'm putting hydro in there. I don't split hairs. Hydro is a green resource. We should use it. We should think of it as such. And then the one nuclear plant that's remaining in California. And I took the natural gas fleet and really tried to understand how it operates as sort of bins of units, because it's not like you have one type of asset or one type of asset which is used in one type of way. You have combined cycle plants and you have You have simple cycle plants, peakers essentially, and then you have capacity factors for each of those. And what I tried to do was take the higher capacity factor plants; those are the harder ones to sort of conceive that you would replace, and translate that to a battery specification. And that's really what I did. I just took a combined cycle gas plant and I said, now pretend that's a battery. What is the spec on it? And so that's where I started.
Mateo, let me just break in there because I want to get on to, and then the technology. But I think it's just critically important. There's two things that I want to highlight from what you just said. And I'm doing this for the audience because they're not all, sort of super expert on, exactly what a combined cycle plant does, what a peaker does, and so on. So we're gonna just dive in there a little bit. And so one thing is, well, the roles of those different gas types. But the other thing that you've done that's incredibly important is you focused yourself, and hopefully through you, I'm focusing my audience on the jobs that have to be done within an energy system. I just find that so often people say, hydrogen is magnificent, and they run around with this kind of hydrogen hammer looking for a nail to hit, and so they start with the technology and then try and find a use for it. And I just think it's so important that we come back to what are the jobs that need to be done by the energy system, keeping the lights on in the evening when the sun goes down, or helping us to fly to California with those, Lotus Elise bodies or whatever it was that you were doing. Yeah. These are the jobs that need doing. And in a system, you've got different sorts of gas plants. So just give us the brief primer difference between CCGT, OCGT, gas peaker. What have you got there?
Yeah, so just to reiterate your point there, which is these are very complex systems, the electric grid, and you have to think systematically if we're trying to solve the solution at the system level, which is, of course, what we care about. So yes, the natural gas system, which is part of the electrical system overall, indeed bins out into different functions. And you have things like peaker plants, which are typically defined as running less than 5% of the time, 5% of the hours of the year. Those are peaker plants. And those are more or less jet turbines strapped to a pad, which produce electricity. They really are that simple. They're not trying to capture emissions really, and they're not trying to mitigate noise, or maybe a tiny bit, but they're sort of the simplest version of electricity generator that you could possibly have.
And those ones you can replace pretty easily with lithium ion. I mean, that's one of the things I talk about a lot, that's just a perfect use case for a short duration. Lithium ion, 5% of the year, it's an hour or a few hours a day. And that one is kind of, in a sense, that's easily dealt with by lithium ion, correct?
That's correct. And you don't want to run it too often because actually your cost of electricity is fairly high and your efficiency is also fairly low, right? So it sort of has a combination of cost and efficiency that means you should use it infrequently, right? But when you need it, by gosh, you're sure happy that it's there. That's for sure. And at the other end of the spectrum from the gas world, you've got combined cycle plants, and these plants are designed to operate at much higher efficiencies and therefore much lower costs. But you want them to run a lot. You want as high capacity factor as possible so that you're amortizing that higher upfront cost over more hours in the year. And ideally, a combined cycle plant is essentially running all the time. And it's 70-80% capacity factors. And it's also being used to provide ramping function. So it does ramp quickly, up and down. These are like F-class turbines that are incredibly powerful and flexible, and provide a tremendous amount of just function to the grid. Right, utility operators love to use them to meet their demand, instantaneously and shift things around throughout the year.
In a way, these are the plants that we'd be using most of if it wasn't for climate change, right? They're big, they're expensive, but they are 55-60% efficient. They are workhorses. But they also they'll do a certain amount of ramping, but they do, to make the economics work, you want to run them a lot and run them fairly continuously. Okay, so those are the ones that you've tried to go after.
Yeah, those are the ones that would be the hardest to figure out how to replace in the system. And so therefore that's a worthy challenge, right? To say, is there a different technology that could help provide that function to the system? We want a resource diverse portfolio, right? For all the reasons that you started to highlight there. It is challenging. It is tricky to think about largely a weather driven energy system, which renewable power is, and all the sort of vagaries and periods of intermittencies and volatility that you then have to deal with. And so absolutely, you want to be able to think about the hardest problem and how you can help supplant that.
Okay, but now you're not replacing on your own the CCGT, these big centralized gas plants. I mean, it is a weather-driven system. What you're doing is filling in then a gap or a hole that neither the sort of, when you've got lots of wind, lots of solar right there, very, very cheap, but they're not there all the time. If it's a short-term outage or maybe just the evening when the sun goes down or something like that, then you can do lithium ion. But you're homing in on a specific period of supply, which is, do you want to, I mean,
that's right.
I can tell the audience, or you can tell the audience, why have you focused on the exact sort of length of duration that you've focused in on?
Yeah, so back to that specification that I sort of took from a natural gas plant, plopped over to a battery, sort of conception. What fell out of that was a couple hundred hours duration, and we started relatively roughly, and I have 4 co-founders, and they're all fantastic folks. We ended up merging 2 very early stage companies together, and one of the guys that is our co-founder, Marco Ferrara, built modeling software, and I don't mean in Excel. I mean very complex co-optimization software. What it was referred to as mixed integer linear programming. Was sort of world-class compute approaches and that kind of thing. And so we started off by saying, let's bound the problem at a couple hundred hours duration, but precisely what does that specification need to look like? And so we started to really zero in on the kind of battery you would need to replace that function. And I say replace, but it also means supplant. The electricity load is growing tremendously, roughly 1% to 2% per year, which means it's going to double. Like the electric demand will double over the next roughly 30 years, which is incredible. And it means that we need all the new resources that we can possibly bring to bear. And so thinking about sort of how you're going to bring the level of reliability and capacity into the system, and as a battery, we have not really conceived of this kind of asset that could participate for those much longer periods of time that we're talking about, days or even weeks on end. And so with this very robust modeling approach, we started to be able to zero down on, there are very specific duration and cost points that are relevant for the grid. And those 2 things are very directly tied, because the cost of energy from a battery perspective directly implies how long you can discharge it for at its rated power. And so what started to fall out of the modeling was 100 hours and $20 per kilowatt hour. And yes, you could envision, let's say, a 2,000 hour battery, but then you're more like 50 cents per kilowatt hour. And that feels like a harder trade-off to make. But it is one that you could say that we have, right? Think about the snow, again, being from California, think about the snowpack in the Sierra Nevadas that we don't pay for, that very helpfully melts over the course of the year, right? That's a very low cost form of energy storage. Or you could even say on a decades long scale, forests, right, which grow for 50 years and doesn't cost anything, or that we're storing energy in the wood, and then you could potentially burn that. But the solution space that we can go after electrochemically sort of puts you in the dollars per kilowatt hour range, and therefore hundreds of hours duration range. And that is the combination of specifications that you need to be able to have to target that function in the grid, right? Those mid-merit gas plants that are running for, flat out for hundreds of hours at a time to provide very valuable resources into the electric system, as well as providing sort of the ramping function. So that's where we started, was to say, that's the kind of battery with that combination of specifications that provides a meaningfully differentiated value from any other type of storage out there, and we know will be valuable going forward.
And I just want to dive in there just to make sure that people are sort of following this trade-off between duration and cost, right? Because, you live batteries. I, have spent quite a bit of time. But this is really because if you have something that cycles, for instance, every day, then the cost gets amortized over many more uses. But if you have something that was only going to be, let's say, once a year, seasonal storage, it would have to be really cheap, because it would be kind of charged up in, September and then discharged in March, and that'd be it for the year. So then it has to be incredibly cheap for that one cycle to cover the costs. And what you're looking at is sort of combining those functions and finding a sweet spot of sorts where $20 and 100 hours, $20
That's right. Yep. Per kilowatt hour.
Per kilowatt hour.
That's right.
And 100 hours, that's going to be a sort of profitable place to land.
That, and there is something that exists in the world that you can build that is entitled to be that cheap, right? Because I could come up with a beautiful specification that does not exist at all in the world, right? In which case, who cares, right? So we wanted to go after something that actually could exist.
Right. So there's a bunch of different things that you could do. You know, you could do $5 per kilowatt hour, and it would be, you could then do 4 weeks. Well, fabulous, but we don't know what that's going to be. Or you can do lithium ion, which already exists. So you've got this kind of 100 hours, $20, and the technology is, we already know, iron air. Talk to me about iron air. What is it? What does it look like? What does it do?
Yeah, so iron air, we say iron air as a battery, really all we're saying is that we're reversibly rusting iron in an electrochemical cell, right? So iron, when it rusts, it's giving up an electron. That's really what it's doing. It's taking on oxygen and giving up an electron. And so if you want to think about it, you know, our bridges, our buildings are very slowly discharging. That's how I think about it.
And presumably they're slightly, that's effectively just running out as heat, right? They are just minusculely warm as they rust. And what you're doing is capturing that, and then you can stick it through a circuit. Am I
that's right.
on the money?
Making it, that's right. Put that electron through a circuit and make it be productive. And then reverse the reaction, of course. And you can, this is maybe the part that most people don't realize, you can reverse that reaction. And how you do that, how you sort of create an electrochemical cell to be cost effective and to be as high performance as you possibly can make it. That's the trick. We did not invent iron air as a chemistry. In fact, it was studied in some detail about 50 years ago in a couple different places. The U.S. Department of Energy paid Westinghouse to do sort of a big seminal study on it in the 70s. Swedish National Lab did something similar around that same time too. So we also didn't have to sort of invent from whole cloth this brand new chemistry. And we knew that the academic literature, which is essentially what that study was, pinned the performance parameters in such a way that we looked at that and said, if we can achieve what they achieved 50 years ago, we have a minimum viable product, right? And we thought, we thought based on our own competence and on sort of modern techniques that we could indeed go and do that. And so that was sort of the fundamental thesis. Let's go embody that technology in a device that can hit the cost targets and the performance targets. Well, they're what they did 50 years ago. So we think we can go do that.
Why didn't they do it 50 years ago? What is new? Have you had any breakthrough? I mean, are you building 50-year-old batteries and going, haha, today they work?
Yeah, indeed we are not. It's not quite as simple as that. But the reason why it wasn't pursued previously, it was studied originally to see if there were automotive applications. Oh. And these are open air, rather they're breathing in oxygen, they're breathing out oxygen. And so, and they're heavy, right? Gravimetrically, relatively low energy density. And so you do not want to sort of use these for motive applications. These batteries would never work for cars, much less laptops or phones or anything else.
Right, because these things are heavy and they're also, I mean, they're big and they don't, talk to me about the kind of energy versus power trade-off that you've had to grapple with.
Yeah, so the other thing is that, in order to get the highest performance of the battery, and I mean that in a lot of different ways, which I'll circle back to, you don't want to put it in a use case where you're trying to get all the energy in or out in a matter of single-digit hours. In other words, 2 or 4 hours, the battery performs much lower across the board in all the ways that matter. If you're trying to use it as what we would call in our industry a high C rate. So all the energy in or out, which lithium ion, by the way, is fantastic at. It suffers very little degradation in terms of efficiency or other things, and it can operate at very, very high rates. Again, that's the ratio of sort of power to energy. So how much energy can you get out? How quickly? And for this application that we're going after, 100 hours is what matters. You need the 100-hour duration, and it sort of flips on its head the approach that we collectively in the battery world have been taking for the last 20 years, which is, how do I do things faster at a higher current density at a higher rate, right? And all of a sudden we're saying, hey, what if we just slow down a little bit? if we slow down, it makes all these challenges that much easier from a current density standpoint, from a battery kinetics standpoint, and so this sort of counterintuitive insight was, if we go after the longer duration stuff, which people say is the harder problem, it actually makes a lot of the technical challenges easier. We get to relax some of those constraints.
So it's summarizing that, is a great big battery, lots and lots of energy. It'll keep you going for 100 hours, but it only kind of trickles out the electricity.
Yeah, that's right. And we use water analogies a lot in the electricity space in general, and in the storage space in particular. The ratio of the spigot to the tank is fixed, in other words. And so you can have a larger spigot, but you're going to have a larger tank to go along with it, right? In other words, that energy travels with the power. And so when we think about the applications here, we are not limited by power, but you're always going to have 100 hours to go with it, right? And 100 hours is obviously, it's a nice round number. Humans like round numbers. So there's probably a bit of a thumb on the scale for that. Should it be 94 hours or 103 hours? Yeah, I don't know. But we picked 100 hours. And the reason for that is 100 hours does solve 4 days, right? Which is sort of where it corresponds to. 4 days does solve the biggest sort of addressable, longer, and I said longer, multi-day duration period of intermittency. That's what you're really trying to solve for. And so going after the 100 hours does range roughly, makes a lot of sense from a solution standpoint. It also what happens to fall out of the math on all this stuff as well.
And an example of that would be Bill Gates and Václav Smil did a sit down, and they were laughing about the idea of powering Tokyo, or powering. They were commenting on the idea of using renewable electricity for Japan, and they said, well, Tokyo, 22 gigawatts, and every so often there's a tropical storm, there's a cyclone, and you have 3 days where nothing will produce. 3 days, they said, you will not do with a battery. And what you're saying is, Bill Gates, Václav Smil, you're wrong. Come visit our factory, right?
Yeah, well, I mean, Mr. Gates is familiar with the company Breakthrough as an investor. In fact, we were their first priced investment. So I think, Bill knows a lot about energy, and I'm sure he wouldn't say, publicly that you can't do it with 3 days. But it is an example for how sometimes you do have to take a counterintuitive approach. And one reason why people say you can't hit 3 days is because of the cost target, the cost implied in the 3 days. But my first reaction to that when I started down this pathway 6 years ago was, well, what can I trade off in pursuit of really low cost? Right? Batteries are full of trade-offs. That's really what they are, sort of a trade-off matrix. and you don't get to have all things at once. You do have to trade things off. But I'll give you one example for how we thought about it. Cycles. In the battery world, we love to talk about cycles. How many times can you cycle a battery? In other words, fully charge and fully discharge a battery. And in the world of lithium ion, cycles are really important because we're using it a lot. We're discharging and charging multiple times per day. If you think about your phone or your car, that kind of thing. But if I have a battery that, let's just say, runs for a week at a time, discharges for a full week, its capacity is 1 week, that means that I could, in the best case, recharge it also in a week, assuming 100% efficiency. And that means a full cycle takes 2 weeks, which means the theoretical maximum number of cycles I could have in a year is 26. And over 20 years, which you want your battery to last as a grid asset, roughly 500, right? So lithium ion does thousands of cycles. They're pursuing 5,000 cycles, right? Full charge discharge with very little degradation this year, now in the world. And for us, that's just not a relevant metric. So I should think about cycles differently. I should think about not optimizing for 5,000 cycles. And what do I get in return? Lower cost, right? And so that's just one way that we have now started to think about the trade-offs in pursuit of the very, very low cost, which really does matter to get the capacity for the electric system.
Okay, now tell me, what do these things look like? What do they? Because they're not little jelly roll batteries, right?
That's right. You cannot hold them in your hand. I'll describe it, but I will acknowledge up front that looking at batteries is maybe our energy transition version of watching paint dry or grass grow. They are terribly exciting, but our devices indeed they're much larger. They are meter scale devices, so it's about 1 meter tall, about 1 meter wide. And sort of tens of centimeters thick. and sort of a plastic vessel. That's what it looks like from the outside. Inside, of course, is where we have the electrochemistry happening. We have iron anodes. So these are essentially plates of iron. They're porous plates of iron, but looks like a large brake pad, if you will. And we have multiples of those inside. And then we have the air cathodes inside as well. And all of that is submerged into a liquid electrolyte. It's an aqueous electrolyte, but essentially a dissolved, high concentration salt that's in there. And that is sort of providing the medium for the ions to move around.
That's your potassium hydroxide, right?
That's right.
Yep. Anything nasty we need to know about that? Is it toxic? Is it rare? Is it expensive? Does it all have to come out of Bolivia?
The answer to all those is no, none. It is the worst thing about it. The electrolyte is that at the concentrations of the dissolved potassium hydroxide, it is very basic. So it's about a 14 pH, and so you don't want to splash it in your eyes for sure. But it is the kind of material that we collectively know how to deal with and do work with all the time. So it's not particularly nasty stuff. It's like Drano, more or less.
Okay, and then you package all of this up into basically a shipping container, right?
That's right. And so those cells go into groupings, which we call modules, which is sort of this industry standard term. And then those modules go into a shipping container. And then those shipping containers from the outside are what you would see at a deployment. So we have N number of shipping containers depending on the size of the installation that would be needed. That's basically the standard for the storage industry today. Lithium ion from the outside would look exactly the same. Just about any other battery that's deployed is going to look very similar from the outside. You've got your grid connected stuff, your switchgear and your transformer and your power electronics, and then you've got your batteries inside of containers.
Okay, but if I had one of your containers, how much power and energy, and a lithium ion container, how much power and energy?
So lithium ion these days, out of a container, you're getting maybe 10 or 20 megawatt hours. Sort of depends on the duration that you're going for. I mean, usually you have like from 1 hour all the way up to 4 or even 6 hours these days. So the numbers do move around a little bit. But let's say you're sort of in the tens of megawatt hours per container. And for us, we're under 10 megawatt hours, depending on our configurations, also sort of between 5 and 10 roughly. But again, from a power basis, we're much less than that. Lithium ion, of course, is going to have much more power and less energy. We'll have less power and an equivalent about more energy than what lithium ion would have.
But the main difference is going to be, so you've got a bit more energy, or maybe even a bit from your description, might even be a bit less. Basically, what you've got, though, is a much, much cheaper container.
That's right.
Right?
Yeah. Yeah, that's right. And we do have configurations where we do have more energy than lithium ion. Again, on an energy basis, you can get it. You can't get it out all quite as fast, but it is much lower cost. Again, we're going after that roughly $20 per kilowatt hour range, and we expect to be there within a matter of years. Our very first projects are not going to be quite that low cost, but we're also not off by an order of magnitude. We're off by percentage points.
Okay, so you've got this shipping container, looks like lithium ion, contains maybe a bit less, maybe a bit more energy, but then discharges at a much lower rate, but is cheap.
That's right.
Can I ask, you say you're not quite at the $20 target, but you're not off by an order of magnitude. Can I push you a little bit more on that? Where are you? And then that leaves quite a big space. You're between 20 and 200. Where are you?
Yeah, we're under 100. I'll put it that way. With the very first deployments that we do.
Right. And how big are those first deployments? What's the scale of those first ones?
So these are sort of 10 to 15 megawatt projects. And these are projects that we're deploying with utility partners in the United States. Our first market is the United States. And these are for delivery in 2025. So starting by the end of next year, we'll deliver to utility customers. And these are real contracts. They've been regulatorily approved. So they have to go to their commissions and get them approved. Which means that they do have to show the costs, and they have to show that they're reasonable and justifiable, and that the long-term cost entitlements are also there. right? They have no interest, just as we have no interest in doing dead end type projects. And so the initial costs are in line with how we show that we get down to the entitled cost.
And so let's take a 10 megawatt deployment. How many shipping containers are you talking about? Because 10 megawatts would be, if the average house is a couple of 100 kilowatts, so you've got kind of 5 houses is going to be, 10,000. So, I'm trying to sort of translate what is 10 megawatts. It's kind of a small town, like one village or it might be one neighborhood, right? But how many shipping
10
containers
megawatts,
are you talking about?
10 megawatts would be a couple hundred containers. And maybe it's also helpful to think about sort of from an acreage perspective, like an areal density perspective. 10 megawatts will be a few acres. We're still dialing in the exact sort of density from a land basis there, but roughly 3 to 5 megawatts per acre. That's sort of the range that we're in right now. Just to give you sort of point of comparison, wind and solar are sort of 1/5 megawatts per acre, and coal roughly 1 megawatt per acre. Natural gas can get up to 30 or 40 megawatts per acre. So we are more dense than, or rather, we're sort of right there, smack dab in the middle of the spectrum, I would say.
So did you say how many acres was your 10 megawatt deployment? Sorry, I was just doing maths on the number of homes. It's 5,000 homes. How many acres would it be for 10 megawatts?
For 10 megawatts, it's probably going to be about 3 acres.
3 acres. Okay. So you've got a village or a town of 5,000 homes, and then you've got a 3 acre plot, which is just shipping containers, one next to the other. Is that a kind of decent mental model? Okay. And which is kind of cool. But then the question is, what happens when it's not 5,000 homes? What happens when it's, I don't know, Pittsburgh, PA, which is how many people live there? A couple of million,
Yeah. So this is where it's important to keep in mind the portfolio perspective. We're trying to solve a system, right? And one of the benefits of having this type of asset in your system, in other words, very low cost and therefore multi-day duration energy storage, is it relieves a tremendous amount of pressure on the overbuild from the renewable perspective. And we see this over and over again in the modeling that we do with our utility partners. And as a rough rule of thumb, when you have this type of asset available to you to optimize your system, your demand to build the renewables drops by about half. In other words, I need half the land to build solar than I need if I don't have this type of resource available to me. And so does it take up land? Absolutely. As part of a portfolio, does it dramatically reduce the demand on the amount of land that I need overall? Absolutely.
Right. And now the audience almost, there will be, by the way, there'll be some people who've done more energy modeling than you or I, and maybe even than your co-founder. There are some real specialists, but most of them won't have done. And they won't realize that these kind of deeply renewable systems where you get to 60, 70, 80% renewables, you start having a lot of overcapacity. You start building 2, 3, 4 times as much renewables, and storage really brings that down, as you pointed out, whether it's the short duration, the lithium ion in vehicles or grid connected. But what you're saying is that extending that out to the 100 hours, you don't need much of that to really push down the overcapacity, the overbuild.
That's absolutely correct. And you make a good point as well. We also don't, cost-effective multi-day storage also does not crowd out lithium ion. You want lithium ion in your system as well, because again, you're co-optimizing across these different types of assets. And, lithium ion has a very different profile, or frankly, anything that's going to compete with lithium ion. I use that as a proxy. It could be, some great flow battery may show up and be cost-effective in that range, sort of 10 to 12 hours. But you also want that multi-day storage. And you want that in the end because you're trying to, again, optimize a system. And we know that we're going to have multiple types of assets, multiple classes of the same asset, because that's exactly what we've ended up with the natural gas side of things, right? Again, back to sort of the peaker combined cycle plant, the co-optimization of those two very different types of assets has led to the least cost, most reliable system. So something similar we expect to happen on the battery side.
So you slicing and dicing those sort of jobs that the energy system has to do, you've matched it, it's fantastic. But there will be people listening to this who say, this is all such nonsense. The answer is nuclear. They're talking about megawatt, 0.2 megawatts per acre, 0.3, etc. And then there's nuclear, which is I don't know, potentially there's many tens of megawatts per acre, and completely eliminates all of this complexity because you switch it on and it just works. And what do you say to them?
Well, I think we should build as much nuclear as we possibly can build and keep all the nuclear on that we have currently running. It's a tremendous resource. But we also need to build things very quickly. And we also need to deploy at very, very large scales. And having another type of asset only helps to solve all the challenges that we have on the electric system. So that's generally how we think about it at Form Energy. It is not, there is no panacea for the grid. There is no single thing that you can conceive of that will just solve all the problems. And nuclear is included in that. It has its own challenges, right? Whether you're talking about fission, large scale centralized fission, or you're talking about small modular reactors. One of the biggest challenges right now is cost. And, you just saw that NuScale had to pull out of a project very prominently and very, I would say, unfortunately, because we need these kinds of assets to show up. What is a fact, a feature of the electric system today is that the renewables are very, very low cost. And what we need to do is help figure out how to turn those into dispatchable and deterministic resources. And having multi-day duration storage allows us to do that. And so we're going ahead no matter what. I hope that nuclear is able to come on and show up in meaningful new ways on the grid because we need it all, both for the load growth as well as for the decarbonization. But it doesn't change our picture whatsoever. Having a new type of asset, cost-effective multi-day storage, only makes things easier.
Right, and I'm sure that if you did look at the modeling, you'd find that actually this kind of 100-day storage probably plays quite nicely with nuclear in terms of some of the maintenance cycles and resilience requirements there. You used a word there, or a phrase, which is really telling. You used the words large scale. And, you've got your 10 megawatt hour system, which presumably if I multiply by the ratio between power and energy, becomes 10 megawatt hours becomes 1 gigawatt hour system. The world is using 25,000 terawatt hours today. And as you've pointed out, it's going to double in the next 30 years. So there's a huge, huge gap between what you're doing and anything that could be called large scale, correct?
Absolutely. Completely correct. It's sort of mind-boggling just how large the electric system is and is going to be. And it can be daunting starting off as a startup saying, oh, I'm going to have an impact in that world. But that's precisely why we chose the pathway that we ended up choosing. At the very least, there's an entitlement to operate at that scale. You do have to think in the terawatt hour scale. For sure, to think that you could ever have an impact there. And so yes, 10 megawatts is a drop in the bucket. The United States has 1,000 gigawatts of installed capacity, right? About a terawatt of installed capacity. And we'll be adding a ton over the next couple of decades. And so you do have to look at that and say, do I have an entitlement both from a fundamental sort of materials abundance perspective, as well as from a manufacturing perspective? Can I make enough of this stuff? What are the means of production? What are the designs? What are the material sets? All of it, not just the active materials, everything else, right? I mentioned the vessel, right? Well, can I scale that kind of thing? And to have an impact in a relevant time frame, which is the other thing, you do have to say, I could build hundreds of gigawatts, right? That's the scale at which I need to be able to build things over the next, let's say, 30 or 40 years. And so that is indeed where we started. We didn't want to work, I'll speak for my co-founders. We didn't want to work on anything that would not fundamentally sort of scale to that level. Now, can we? I think we can, but we are entitled to go do that, again, from a materials manufacturing perspective. It will take some time, to be clear. And our first factory that we're building, annually will produce about 500 megawatts by roughly the end of 2027, early 2028. That's 50 gigawatt hours. So still a tiny drop in the bucket. But from that point, 500 megawatts per year, we can start to see thousands of megawatts per year, right, gigawatts per year, and then going from there.
Right. You also used a word, you used it in a different context. You said a ton. You've got to do a ton of this stuff, right? Now,
Yes.
one of your shipping containers is 35 tons. That factory, that 500 megawatt factory will use 1 million tons a year of iron. And to put it in perspective, there's about 2 billion, just under 2 billion tons of iron, primary iron production each year worldwide. So, 1 million tons is kind of like order of magnitude starts to actually be, in the same kind of, time zone as the amount of iron that we're reducing. And, I did a little bit of noodling of numbers because I get excited when things can solve, 1% of a problem. And so the numbers I calculated, I'll share with you. I took that 25,000 terawatt hours of electricity, and I doubled it, just as you did. I said, look, the real problem is 50,000 terawatt hours by, let's say, 2050. That's the electricity demand. Maybe 1% will go through this kind of 100-hour storage. That's 500 terawatt hours. Right, so your first project is doing a gigawatt hour. We need 500 terawatt hours. And then blah, blah, blah. I went through my back of envelope, and I worked out that you would be using about, if you were to start producing enough of your form batteries to do that, it would be using about 2% of all of the world's primary steel between now and 2050. Is that really realistic? 2% of all steel going into this?
Well, I would take a slightly different view. I'm going to come back to the number specifically because I think it's important. But I would say if you rerouted 2% of all steel and you solved the storage problem for the grid, that's a pretty good deal. I would take that deal. But going back a little bit on the numbers, it's not quite 1 million tons per 500 megawatts per year. And that's simply because the container is not entirely made of iron, right? There's other things that are sort of going in there for the weight. So it's more like a couple 100,000 tons to produce that 500 megawatts per year. Nevertheless, it is a lot of iron for sure. Iron, except for coal, is the most mined substance on Earth, about 3 billion tons per year. And of that, about 100 million tons per year goes into what's called direct reduced iron. That means it's metallic iron. You take an oxide out of the earth and you reduce it, you drive off the oxygen, you end up with a metallic iron. That is what's used for electric arc furnace steel production today. So we have two major types of steel production, blast furnace and electric arc. Electric arc is what uses that DRI, direct reduced iron, as well as recycled scrap iron. If you took just what is used for the direct reduced iron today, 100 million tons, and rerouted all of that to go into battery making, you would produce roughly 200 gigawatts worth of energy storage. 200 gigawatts translates to 20 terawatt hours at 100-hour duration. Michael, you said 500 terawatt hours per year, right?
Yeah, and of course, I'm only cycling it once. So that's my mistake.
You're cycling it once. Let's cycle it 10 times a year.
Okay.
Right? Now we're down to 50 terawatt hours, right? In which case I need roughly 2.5 years of production from just the direct reduced iron. Now, we're never going to reroute all direct reduced iron, right, into this particular field. But it puts us in the ballpark and says, this is realistic to sort of contemplate, right? You can go build a lot more direct reduced iron capability if you absolutely had to. Now, the implications are also, well, how do I decarbonize that, right? Because steel making needs to be decarbonized as well. And you can think about, yes, green hydrogen, you need a lot of it to go do that. Even more compelling, and which is what is really fun, on the entrepreneurial side, is to say, well, how do we avoid that altogether? How do we just use the oxides, right, directly? Because after all, we are reducing iron inside the battery. And so that's, I'll be candid. I'm not going to share a lot of details on it, but that is one of the really fun parts of being inside of a company that has a tremendous innovation engine to think about these problems and solve them.
Right. So I was trying to do, it wasn't really an attempt at a gotcha, because it's not a gotcha. It was just, the point I was making is it's an awful lot of iron. You've pointed out correctly, it's not quite as much as I thought, probably by a factor of 10. So it might be 0.2% of all iron for the next 50 years. So it's still, but that's still an enormous, that's still a lot. And And it's probably about, if you did do it through hydrogen reduction of the iron, it's probably about 0.2% of all electricity as well, because that's
Yes.
a very power intensive, which actually brings me to the final sort of topic in a sense, which is you're not doing this in a vacuum, right? There are other solutions for longer duration.
That's right.
Storage, whether it's 100 hours or not. And there's liquid air, there's hydrogen, there's high temperature thermal storage. You've got one sort of, I don't want to call it it's not a fatal flaw, but you're not very efficient. Your round trip efficiency is only about 50%, correct?
Yeah, a bit lower, yeah.
Does that give you a sort of discipline? You have liquid air. You have people like Highview Power talking about doing 85%, and the high temperature thermal folk talking about 65%. And the hydrogen people, of course, are much less efficient, but they have salt caverns, right, which are much, much cheaper than iron. So
Sure.
How do you win against those other options?
Yeah, and I would add into the mix, there are substitutes, not just devices that are trying to do the same type of thing, but transmission. If you had a perfectly built out transmission system, you would dramatically reduce your need for storage or carbon capture, frankly. If you could put a magic box on top of the flue gas of a natural gas plant, you would solve all the problems associated with carbon with natural gas. As we talked about already, they're wonderful machines. They're tremendous technology, right? It's the carbon that we really are caring about there. So we see certainly competition coming from all sides. As far as the efficiency, what we have found over and over again in the modeling is the overriding value comes from having the low cost, not from having very high efficiency. Again, because you're doing something different, right, on the electric system. And just as gas peaker plants have very low efficiencies compared to combined cycle plants, that's okay because they're providing a very valuable resource. Well, some similar things are at play for energy storage as well. Now, it doesn't mean you can be 10% round trip efficient and still solve. That's too low, right? But it does come down to trade-offs. So talk about how all batteries are trade-offs and how we should think about trading off the right kind of thing here. And so what we have mapped out very precisely based on the modeling is that curve, which is CapEx and round trip efficiency. And so we understand very precisely, where on that curve we are and what that trade-off should look like. So how should I trade $1 of CapEx for 1 point of round trip efficiency? And how does that matter in the system, right? We talk about in the battery world, all sorts of figures of merit to try and compare things, levelized energy of storage or levelized energy of cost. I would submit to everybody that the only real way to value energy storage or to compare energy storage is in a financial model, in a portfolio driven resource sort of optimization. That's the only way to know whether any of this matters. And so that's what we've done. And that's been our approach from the very, very beginning. And so we know that $20 per kilowatt hour, 100-hour duration, and a little bit less than 50% round trip efficiency solves. That is, you are in the solution space to provide a lot of value into the system. Would you take more efficiency if you could get it? Absolutely. But you better be precise about how much you're willing to pay for every point of round trip efficiency. And we know that extremely well. So
what you're really saying is $20, 100 hours, bring it. If you can beat it, then Form Energy is done. And if you can't, Form Energy is going to win.
Absolutely.
What are the next milestones for you? Just to round it out, what happens next? You've raised a bunch of money. You've got Bill Gates as one of your investors. Has he written you a blank check forever? No. So what are your milestones and what happens next?
Yeah, so our milestones really now are associated with scaling up the manufacturing. And that's really where the overriding focus is. I mentioned I lived in California. Now I live in Pittsburgh. The reason for that is our manufacturing facility is being built about 30 miles from Pittsburgh in West Virginia. There's a northern panhandle of West Virginia, and we're building a factory.
I was going to ask you, is that because that's where all the steel comes from? And since you reuse all the iron, you might as well be right there next to those iron reduction
Not
plants.
only that, we're going into an old steel mill site. In fact, Weirton, West Virginia, the old Weirton Steel Works. which was the largest producer of steel, for example, in World War II for the United States, which tells you something. They employed 14,000 people.
I love the historical sort of connective tissue. Okay, but go back to what are your milestones? What happens next?
So it really is around the scale of the manufacturing side. So that plant is being built. It was an old steel mill, like I said, but it's been taken down. It's a brownfield site. We're building it back up. And our first customer deliveries will start in earnest in 2025. So we've announced projects with a handful of utilities here in the United States. Again, those are contracts we have to deliver. And they're in sort of that 10 to 15 megawatt range, 5 to 15 megawatt range, depending on the utility. And so that's really the key focus. That will be our full market entry. We'll be delivering in 25 in the United States, and we expect to start to deliver into Europe relatively shortly after that. So 26 is when we expect to see those first markets. Perhaps not surprisingly, as you would guess, the island markets are the most compelling markets for us right now in Europe. Ireland in particular, and then in its own unique way, because everything is special about it, the UK shortly after that.
And you have a team here already, right?
We do, yeah. We have a couple folks, and they're working on policy, they're working on market entry, and they're working on analytics to make sure that we really deeply understand that market and how it all dovetails in there. And things are moving quickly across all those fronts there. Of course, there's a tremendous amount of governmental support that is there or coming, and the market designs are also evolving fairly quickly to be able to take into account these new kinds of resources. And the operating facts on the ground are saying, hey, we need this kind of storage to show up. Think about all the offshore wind in the North Sea or adjacent there to Ireland, for example, and the constraints on the grid today, tremendous load growth, constrained nodes, and highly variable renewable resources. That's a sort of a perfect mix for us to show up into that market.
Do you not have to be careful if there are salt caverns that could end up being filled with hydrogen? Does that not sort of destroy the market for you? Do you not? Because I've just been in Japan. They have no storage solutions that are obvious. And so they're going to have to kind of create them from nothing. That's very different from the UK, which does have huge amounts of potential hydrogen storage.
Yeah, I mean, there's certainly you could store a lot of hydrogen there. You also need to figure out how you're going to burn it efficiently in a turbine. And so this is sort of the next big puzzle that's got to be there. And those geologic resources have to be in a very handy location. You can't really afford to move it. And so, there's a lot of challenges that need to be solved there, which is typical, right? And all we're focused on, and all we can focus on, frankly, is how quickly we come to market and how we prove that the solution works. It works, and we're going to show folks.
And in fact, you missed a trick when I asked about the liquid air storage and all these other options. Yours just produces electricity straight back through the same connection that it came in, as opposed to needing a generator to go along with it. So there you go.
That's right.
I'm rehearsing your lines for your next podcast for you there.
Yeah. I mean, it is a wonderful thing about electrochemical cells. They are extremely deployable, right? In the end, especially when we're working with such benign materials like what we have. It's one of the benefits, right, of the approach to sort of electrochemical storage, and that has huge impacts on the speed and scale with which you can deploy. Right, you don't have to look for sort of this perfect set of geologic conditions to make the project pencil.
Fabulous. Look, it's been a great pleasure talking to you. Thank you so much for spending some time on cleaning up. And, I wish you luck, and I look forward to tracking your progress and checking back in with you as you hit those milestones, or not. But I've got a feeling you'll do just fine. Thank you very much. Thanks, Mateo.
Thanks very much, Michael. Pleasure to be here.
So that was Mateo Jaramillo, co-founder and chief executive officer of Form Energy, which is developing 100-hour electricity storage based on an iron-air battery chemistry. And as always, we'll put links into the show notes so you can find out more about the company and about the guest. And those of you who are interested in long-duration storage will want to catch episode 122, which was with Professor Sir Chris Llewellyn-Smith, and he was talking about storing hydrogen in very deep salt caverns. If you've enjoyed today's conversation, please remember to like, share, and subscribe to Cleaning Up or leave us a review on your chosen podcast platform. And do please spread the word on social media or by telling your friends and colleagues. And if you want more from Cleaning Up, sign up for our free newsletter at cleaningup.live, where you'll find our archive of over 160 hours of conversations with extraordinary climate leaders. Cleaning Up is brought to you by our lead supporter, Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation.